Hello everyone, and thank you for joining our webinar, which will provide background on use of activated carbon for sediment remediation and introduce a new modeling tool to evaluate in-situ caps to sequester PCBs and PAHs in contaminated sediments. This webinar was a joint effort of Cabot Norit Activated Carbon and AquaBlok. We plan to cover today's agenda in about 30 minutes, after which we'll address audience questions that you've submitted through the online tool. The webinar is being pre-recorded and will be hosted online for you to view at your leisure. We'll start by providing an overview of the application and technology, then introduce the CapSim model, and finally cover the online calculator tool that serves as a simplified front end to CapSim. I'm Ken Koehlert, the Product Line and Technology Director for Norit Activated Carbon. Norit is the world's largest volume producer of activated carbon, manufacturing for over 100 years at sites in Europe and North America. Norit is the largest producer of powdered activated carbon and second largest producer of granular activated carbon in North America.
I'm John Collins. I'm General Manager of AquaBlok. We've been making patented composite material products for sediment remediation for over 15 years. We have over 200 project locations, and we've been manufacturing these materials both domestically and abroad. I'm going to start off our presentation with an application overview, and then I'm going to hand it back to Ken to tell you a little bit more about activated carbon. Okay, so why are sediments important? Essentially, it's because they function as a natural repository or reservoir for contaminants. Many of these contaminants are bioaccumulative, meaning they can be ingested and transferred up the food chain. This makes them a significant ecological and human health concern. The EPA has recognized that remediation approaches, other than conventional dredging and capping, can be employed which are much less disruptive and can dramatically reduce risk. This presentation will focus on one such method, the application of activated carbon. When applying amendments, such as activated carbon, a key difference from conventional cleanup methods is that we were focusing on pore water concentrations of contaminants. This is versus bulk chemical concentrations. This is because we know that both ecological and human health risks come from the bioavailable fraction of these contaminants. We are addressing the health of the benthic community and limiting the ability for contamination to bioaccumulate and move up the food chain. It is important to understand it is only possible to achieve reductions in pore water concentrations of certain key contaminants with activated carbon. These are primarily hydrophobic contaminants, but also include some metals. To be successful, the activated carbon must have the proper physical characteristics to match up with the target contaminant. But there will be much more on this topic to come later in the presentation. Early in the development and demonstration of activated carbon technology, there was not necessarily agreement that pore water reductions would provide the desired reductions in uptake of contaminants by the benthic community. However, we now have many lab and field demonstrations that show exactly that. While some regulatory community have been slower to recognize this benefit, at the federal level, EPA has embraced this as an important risk reduction approach. A number of industry trends are influencing the shift to in-situ treatment over conventional remedies. Cost is important, but beyond cost, it is being recognized that dredging and essentially relocating the contamination is not a sustainable approach. In addition, there's a continued push to reduce residual contaminant concentrations, often in areas where dredging or conventional capping is not practical or will destroy high-value habitat. It is expected that there will be a continued growth in low-impact approaches that can be monitored and improved over time. This is the adaptive management concept being put forward by the U.S. EPA.
Now we'll cover an overview of activated carbon technology and cover some important points for practitioners to consider when choosing an activated carbon type for such projects. Activated carbon is a highly porous carbonaceous material. It has a very high internal surface area. If one were to flatten out the surface area from all of the pores in 1 teaspoon of activated carbon, it would cover a football field. This is an indication of its high adsorptive capacity. Steam or chemical activation is used to create the pore structure within the carbon source. Norit makes over 360 unique activated carbon grades. We design and manufacture them to remove specific contaminants in a wide range of applications. A product that works in one application oftentimes does not work well in another. We make activated carbon from the widest range of feedstocks of any manufacturer. We are agnostic as to whether we sell powder or granular, and we are indifferent as to which feedstocks we use. Heading into this project, we wanted to identify the best solution and develop a tailored grade that worked the best for sediment remediation. This video depicts the adsorption process in activated carbon. First, there's mass transport of impurities through the water to the particle surface. Next, there's diffusion of impurities into the pores. Then, adsorption of the impurity to the pore wall. This video also shows the importance of the distribution of small, medium, and large pores and how they interact with various size contaminants. Here we summarize the key findings from our research. First, the interplay between capacity and kinetics. The theoretical capacity is the same for both PAH and GAC forms, but utilization of GAC capacity may be reduced by slow kinetics. Second, because kinetics can be important, the choice of PAH or GAC form depends on the specific contaminant and cap conditions. For example, adsorption of hydrophobic organic contaminants, or HOCs, is much faster with PAH. In situations with high upwelling rates, PAH is preferred because kinetics then become important. Third, natural organic matter, or NOM, is an important factor in many water bodies. NOM can block pores and limit contaminant adsorption. This impact depends on carbon pore structure. For example, coconut carbons have a fine pore structure that can be easily blocked by NOM, resulting in poor contaminant removal performance. However, the broader pore size distribution of a lignite-based carbon maintains its performance in the presence of NOM. Finally, there are two limiting cases of performance. In diffusion-dominated systems with no upwelling, all carbons give similarly good performance. At the other extreme, with high upwelling, all GACs have similar but poor performance and rapid breakthrough. Between these two limits, activated carbon feedstock and form become critical design variables. Norit developed and commercialized two grades for this application: Sediment Pure PAH and Sediment Pure GAC. Because of the physical properties, powdered activated carbon cannot be placed directly into the water column. PAH must be used with a delivery system such as AquaGate plus PAH. This will enable it to be delivered to the contaminated sediment surface. Granular activated carbon is most commonly deployed in a sand-GAC mixture or slurry. GAC can also be applied directly to the sediment surface. Finally, GAC can also be added to geotextile mats, which are anchored to the sediment surface. Setco and Husker are two companies that make these products.
All right, Ken's given you some background on activated carbon. Now I'm going to pick up the ball and we're going to talk about some key design issues. Now, the question is how to employ activated carbon. We feel it's first important to understand some of the fundamental design characteristics that will influence how activated carbon is incorporated into a remedy. Some of these key issues are shown on the graphic. The first, and probably the most important, is uniform distribution of the activated carbon within the sediment or the capping layer. It's important to understand this is a contact sport. In other words, contamination must be in contact with the activated carbon for the adsorption process to take place. As a result, residence time will determine contact time. This is an issue related to the speed of upwelling. That means that the thickness of the layer may need to be increased to provide sufficient contact time between the contaminants and the activated carbon. Finally, it is important to understand that non-uniform movement of pore water contaminants through the sediment or through the capping layer is likely to take place. This means you may need to adjust layer thickness to account for that, and that it's possible that there may be more rapid saturation of activated carbon or use of activated carbon capacity in discrete zones that have higher contaminant concentrations. So here's what in-situ treatment looks like in the sediment. What you're seeing in this slide are photographs that show a side view or a cross-section of sediment before and after placement of our AquaGate Plus pack, that's powder activated carbon amendment. The powder activated carbon is delivered to the sediment as a coated aggregate particle, and the pack comes off the particle and is mixed by natural bioturbation into the underlying sediment. The uniform distribution of the pack and the sediment is apparent, and this is what results in the pore water contaminant concentration reductions. This slide presents an example of reductions that can be achieved using powder activated carbon in sediment. The Navy has been a big proponent of in-situ treatment technology, and much of the field data we have comes from Navy sites where activated carbon has been applied. This is one such example. At this site, two pack delivery approaches were compared. As you can see from the chart on the left, pore water concentrations were reduced from between 62 and 75% with the application, and this resulted in corresponding 80% plus reductions in PCB concentrations in a target species, the bent-nose clams. These results have now been duplicated at a range of sites throughout the world. So now that we've convinced you that investigating activated carbon-based approaches for sediment remediation makes sense, the next question is, how do you approach this? For many in the industry, the CAPSIM model has become a standard. However, to use this model, partition coefficient information is required. For this reason, AquaBlok worked with Cabot to develop a range of data that we felt would apply to the widest range of possible applications. This slide represents a range of that information, some of which has been used to develop the Cabot modeling tool that will be further explored in the balance of this presentation.
As John mentioned, we'll now switch gears and review the CAPSIM model. Danny Reibel is the Donovan Maddox Distinguished Engineering Chair at Texas Tech University. He's a renowned expert in the field of sediment remediation. He and his research group developed the CAPSIM model, which is widely used by engineering firms to design remedial caps. The CapSim model is designed to simulate contaminant transport through sediment caps. It is an extremely robust tool with the capability to model a broad range of conditions. The CapSim model is accepted by the regulatory community and has been widely used by engineering firms to design solutions using activated carbon for sediment remediation. A downside of the rigorous CapSim model is the calculation time of about 40 minutes for each scenario. The goal of our work at Cabot Norit was to give practitioners a fast and easy way to access the power of the CapSim model. The two main gaps were in equilibrium and kinetic data for specific PCBs and PAHs, and information on the impact of parameters such as activated carbon form and feedstock, and natural organic material impact. John discussed how we closed the first gap with lab data. The second gap was closed by running hundreds of CapSim scenarios and correlating the results. Now we'll discuss how the calculator tool was developed and how it can be used to quickly and easily assess cap designs. Here we see the set of parameters and the range for each that was analyzed by our team. Professor Reibel and industry experts like John provided guidance and direction for the parameters and ranges above to reflect typical application conditions. Choices had to be made to cover the broadest range of realistic cases while keeping a reasonable calculation burden. After running well over 500 CapSim simulations with sediment pure activated carbon, a neural network model was developed using the JMP statistical software. About 2/3 of the CapSim data were used to train the model, with 1/3 reserved for testing and validation. The model results are visualized through an HTML-based interactive calculator tool. The model has an R-squared value of 94%, which means that it is highly predictive of CapSim for sediment pure activated carbon for the parameters and ranges listed on the previous slide. We host this calculator on the Cabot Norit website for you to use at your convenience. On the same site, we host an instructional video, user's guide, and related marketing materials like data sheets and an application brochure. Here's the user interface for the calculator. The key output is the y-axis on the leftmost plot, which shows the percentage of the original contaminant concentration at the top of the cap at the selected design life. The inputs are shown across the other plots and can be varied either by dragging the vertical pointers or by clicking on the value and typing it in. The 6 variables covered include contaminant type, form of carbon, PAH or GAC, percent carbon in the cap, the upwelling rate, the cap thickness, and the cap design life. Now let's look at an example using the calculator. We select naphthalene as the contaminant of interest. We select granular activated carbon at 10% activated carbon in the cap. This site has an average 2 cm per day of upwelling rate. We select a cap thickness of 20 centimeters. And we want the cap to last for 60 years with no breakthrough of the contaminant. The output shown in the y-axis in window pane 1 indicates that 11.5% of the original contaminant concentration in the sediment will reach the pore water at the top of the cap layer in 60 years. This is clearly not a robust solution, as there is significant breakthrough. Now let's make one change to the design from the previous example. We'll change from granular activated carbon to powdered activated carbon in the second plot. Now the y-axis in window pane 1 indicates 0% breakthrough. This is a robust cap design. In this case, due to the fast upwelling rate, a powder outperforms a granular due to the improved kinetics that you get with a powdered activated carbon and its small particle size. As an alternative to using the calculator, engineers could take the partition coefficients that we provided in the earlier slides and plug them into the CapSim model. The simulation would run for about 40 minutes, and then one would need about 20 minutes to interpret the results. The CapSim output and the output from the calculator shown above would be very similar due to the high correlation coefficient of 94%. Let's look at another example. Here we make the selections PCB 18 contaminant, GAC at 5% loading in the cap, a 1 centimeter per day upwelling rate, cap thickness of 15 centimeters, and we want the cap to last for 100 years without breakthrough. We see on the y-axis in window pane 1 that 28% of the original contaminant concentration in the sediment will be in the pore water at the top of the cap 100 years later. This is a very high breakthrough and is not a solution. Next, we change two variables to see how these changes affect the performance of the cap. First, we'll increase the carbon percentage from 5 to 15%, and we'll double the cap thickness from 15 to 30 centimeters. We now see that 4% of the original contaminant concentration will be present in the pore water at the top of the cap 100 years later. This is better, but still not a robust solution given that there is breakthrough. Staying with the same example, we find that if we switch from granular to powdered form, we're able to design a cap without any breakthrough. In fact, we find that we can reduce the carbon down to 3% and the cap thickness down to 5 centimeters and still prevent breakthrough 100 years later. This is a robust design, and one that will be far less expensive than the other two GAC options that we analyzed that did not result in robust solutions. This is a great example as to how the calculator can quickly enable engineers to home in on the feasible set of robust cap designs for remediating contaminated sediments. We're hopeful that you find the calculator to be valuable, and we'd like to encourage you to use it. Here are the instructions for gaining access. You can also find this information under the reference widget on the console. Just remember to go to sedimentpure.com. To summarize, Cabot Norit developed an easy-to-use calculator that correlates very well with Danny Reibel's rigorous CapSim model. The calculator tool enables engineers to quickly screen a number of cap designs and estimate the effect of 6 factors on contaminant breakthrough and cap design lifetime. Finally, Cabot Norit has developed sediment pure activated carbon in PAH and GAC forms. These carbons are effective in reducing PCBs and PAHs in the presence of natural organic matter. We've prepared a video tutorial that provides a good overview of how the calculator tool is used. You can access this video from the reference widget at the bottom of the console. If you'd like further information, please contact Billy Barron at Cabot Norit Activated Carbon or John Collins at AquaBlok. Thanks for participating in today's webinar. John and I will now address questions that have come in throughout the session. Well, thanks everyone for listening. This is Ken Koehlert. I want to take a question that came in from Eli. Why is lignite carbon less affected by NOM than coconut shell carbon? It's a great question, and it comes down to the pore size distribution within the carbon. The coconut carbon has a fine, narrow pore size distribution. This gives it a high capacity, but makes it easily blocked by the larger molecules like NOM. The lignite carbons, in contrast, have a combination of macro, meso, and micropores. So think of it as larger pathways to allow access to the inner capacity of the carbon. So that structure allows it to be more resistant to the larger NOM molecules and retain that capacity. Over to you, John.
Okay. I got a question here from Steve, and perhaps Ken, you'll want to comment on this as well. But Steve is asking about the impact of NAPL on activated carbon, the presence of NAPL. That's a great question. And activated carbon is really used particularly in dissolved phase type applications as opposed to NAPL. A pure phase contaminant will tend to block pore structure of the activated carbon. A lot of times in situations where we know that there's going to be a high degree of NAPL, we'll combine or do kind of a treatment train approach and maybe use organoclay-based materials in front of activated carbon. We've done that both in sediment applications and in permeable reactive barrier applications where we knew NAPL was present.
Okay, we've got another question here on activated carbon. And the question here from Dan is, how did coconut shell-based activated carbon perform for sediment remediation? So if we look at this in a high purity DI water system, the coconut shell-based carbons worked great. But once we got to having small amounts of the NOM material in the water matrix, there's a significant degradation of performance with the coconut carbons. We saw about as much as 75% degradation in performance going from pure deionized water to 25 ppm of NOM in our laboratory testing. So that's why we didn't pick the coconut carbons for our product offering. And these results are really consistent with the types of activated carbon that we use in other water treatment applications. We almost never see coconut-based carbons in potable water or wastewater treatment because the background organics partially or completely block the pore structure. John, back to you.
Okay. We got a question here on PFAS, which is a good question, hot topic these days. And the question basically was between the two companies, are there amendments in our toolboxes that are available for that? The answer to that question is yes. Actually, both companies, both Cabot and at AquaBlok, we have different types of materials that are available for different types of applications. Cabot has done a fair amount of work in that area and can provide some information on that for activated carbon. And on the AquaBlok side of things, we're supplying a material called Rembine, which is from Australia, and it is essentially a combination of activated carbon with aluminum hydroxide, some other materials that provide ionic bonding sites for those contaminants. So yes, I would encourage anybody that's interested in those to contact either one of us, and we can provide more information on that.
Okay, we've got a question here from Deirdre. Are the results of the isotherm testing available in a report? We do have those partition coefficients available on our website and also available in the reference material.
All right. I've got another question here from Rich, and his question is in relationship to how we're measuring these percentages. The question is, when you refer to percent PAC or percent GAC, what is the basis, volume, or weight? And it is weight. It is weight based, and it's either based on the dry weight of in the case of in situ treatment, we always look at the dry weight of the layer of sediment that you're trying to address, or in the case of a capping layer, it would be the percent of the dry weight of the capping material. And this really raises a really interesting question, because it's very difficult when you look at GAC sand mixtures to get a good, reliable both bulk density and weight for some of these sand materials that are being mixed with. Oftentimes we ask that question. We say it's easier to look at it sometimes in pounds per square foot, for a given layer thickness. So that's something that we talk about all the time, and we encourage the engineers and the folks that are speccing these materials to think about how much carbon do you really want in there, and come up with a way that we can communicate that's easier for the contractors and folks that are trying to price out the actual solutions to work with, because there tend to be very large variances in the specs for some of these capping materials that we're mixing activated carbon with. So thanks for that.
Okay, I've got a question here from Dave. Are there specific types of situations or conditions where the sediment pure diverges from CapSim, or are the differences random? So the way we develop this neural net model, we really work to randomize those differences. So if we looked across the whole range of parameter space that we explored using actual CapSim runs, we really set up the model to minimize those deviations across the whole space. So should be good across the board. Thanks.
Okay, I've got a question here from Matt, and the question really relates to I think it relates mostly to the stability of the materials as installed. And the question, I need to find it again. Oh, hold on. The question is, do you have any information on winnowing or erosion of PAC once disaggregated from the AquaBlok or the sedimite? He's really wondering about stability in the sediment over time. That's a good question. Typically, when we talk about in situ treatment, we're talking about relatively speaking lower energy environments. For that very reason. If you're trying to use activated carbon in a capping scenario or an in situ scenario where you have relatively high flow rates, or it's a flashy situation, it's probably not going to be as applicable. Although if you give the activated carbon a chance, if there are low flow time periods of say 3 months, 6 months during a calendar year where those that activated carbon can become reasonably well mixed with the underlying sediments, then those materials can stay in place even in a river or a flow situation for a long period of time. And I know that some of that testing was done up on the Grass River with some of the original activated carbon that was placed up there. And there have been sites where materials have been placed directly on the sediments that they've gone back 5 years or more and verified that the carbon's still there and doing what it's intended to do. So there is some data available, but it's I think a question of it's obviously a good question of matching the type of capping material and the type of remedy, whether in situ treatment versus capping, to the task at hand and the setting.
Okay, we've got a question here from Matt about the grain size ranges for the GAC and PAC products. So this information is available in the data sheets at sedimentpure.com, but our powdered product is a minus 325 mesh powder. The GAC product is a granule. It's minus 8 mesh, probably about 8 by 40 mesh size. So thank you.
I've got a question here about monitoring and maintenance of these types of applications. Again, really good question. I'm going to take the maintenance side of it first, just because I want to comment on really the importance of quality control and quality assurance when you use these materials, and I think it's important to make sure that you achieve, first and foremost, you want to achieve what the design intended, right? So, Rich asked the question about, how much carbon, and how do you determine the amount of carbon. We want to make sure that you apply post-placement, that immediately post-placement how much material you put down, and that you verify effectively what was designed and what was constructed in the field. So once that gives you a baseline, similar to the same concept behind, knowing what your, pre-placement, contaminant levels were versus what you're trying to monitor and compare to. So that's the same concept. So first know what you constructed and make sure that you verify what was done by the contractor and that you met the objectives of the design. After that, you can go back after the fact and you can take samples of sediment and you can determine, what the carbon levels are in the sediment. But, I guess, we're less concerned about that over time as we are knowing whether or not the remedy worked. And that's really the monitoring side of things. And really the technology that really has been applied fairly successfully so far is sediment pore water monitoring, via passive samplers. And really what we're trying to do, as I suggested at the beginning of the presentation, is we're trying to get the bioavailable fraction, the pore water contaminants, reduced from the pre-remediation levels, the post-remediation levels. So we think, from a monitoring standpoint, we really want to focus on pore water and track that over a period of time. And if we do that, then the other types of monitoring methods where we're looking at things moving up the food chain and impacting fish tissue and other things like that should respond over time, although there could be, somewhat of a delay between pore water reductions and fish tissue reductions. But those are great questions and very important questions, and we could probably do a whole separate webinar just on that. But we'll move along for now. Thanks.
Okay, we've got a question here from Rich on the meaning of PCB 18 in our example. So we picked a wide range of contaminants with the help of Danny Reibel and John, and PCB 18 is one of those specific congeners. So hope that helps. Back to you, John.
Okay. I have a question here about, hold on a second, I got to get to it. Sorry, I'm having trouble. Okay, I got to it. Sorry about that. This question here from Summer: is activated carbon mixed with sand in an application for PCB remediation Activated carbon can be mixed with sand. If you're going to mix activated carbon with sand, it can be mixed in a number of ways. It can be mixed in the form of a Aquagate plus PAH product. That's the way that we've promoted and we've done it because it helps the activated carbon stay mixed with the sand while being placed through the water. However, there have been applications of granular activated carbon mixed with sand, and those have been successfully placed as well. It really gets back to, and those have been for PCB remediation in both cases. So it really gets back to the conditions at the site as to how you place these materials. But like I said, it's important to understand what it is that you're trying to accomplish from a construction and design standpoint. But yes, that's the answer.
Okay, another question from Rich. Is the model tool only applicable to PAH or GAC? What about organoclay? And we developed the model based on our CapSim simulation runs using the sediment pure PAH and GAC. So the model is really only applicable to those cases. Thanks for that question.
Here's kind of an interesting question. Question is related to how is capping with artesian conditions handled. Artesian conditions, I guess would suggest, isolated flow, like much higher isolated flows coming up through the sediments. And I think that that's obviously a very difficult thing to address, and it's very site-specific. It is possible to place materials over much higher upwelling areas like that, but it would require very specific designs, and you'd have to know quite a bit about the conditions that you're trying to deal with in order to really address it properly. So can be done, but is something that would really require a lot of study and work to really do appropriately.
Okay, we've got a question here from Karen about DOC versus NOM. So typically we measure DOC concentrations in pore water. How does the 25 milligrams per liter threshold for NOM, which we typically do not measure, compare to DOC? Well, we don't have, I think, a comparable measurement. We've used a standard NOM material from the Suwannee River. That does have some insoluble matter in it, so I'm sorry I don't have the breakdown between soluble and insoluble.
Okay. I've got a question from Andy here. The question is, are there any studies of in-situ long-term performance of carbon-based caps? And this is a situation where long-term is kind of relative. This whole area, the whole study of activated carbon and sediment remediation is pretty new as it relates to sediment remediation in general. So, if you mean, by long-term, decades, kind of thing. And I've had people, say to me routinely, in the industry, well, come back and talk to me 50 years after your stuff's been down because, if it doesn't work for that long, I don't want to talk about it. But, the difference here with in-situ is that, we're seeing very positive results in very short periods of time. Which can have a really positive effect, on the areas that the materials are being placed. But to answer the question, the longest term data that's out there right now is what I mentioned earlier. There's some information that's been released on Grass River, where some of the earliest demonstrations of activated carbon were done. almost a decade ago, and they've gone back and they've been able to find activated carbon in the sediments, and they know that it's still functioning, and the areas where the carbon was applied, has shown, lower pore water concentrations than other areas in the river system. So from what I know, that's about as far back as it goes as far as long-term performance for activated carbon at this stage of the game.
Okay, got a question here from Dave. Does your calculator tool allow one to simulate direct application of GAC or PAC without a sand cap? And the answer is no. We did all of our simulations based on mixtures of PAC or GAC within the sand cap layer.
All right, I've got I think one last question for me, and that is a question about the measurement of upwelling rates. As we've discussed here, a critical aspect of modeling and design is knowing what the rate is, and that's something that has to be it's an input that has to be entered into the modeling calculations. And my understanding, I'm not an expert in this area at all, but my understanding is that that's typically done with piezometers. There's other methods you can take. You can look at the nearshore groundwater flux rates and assume. Sometimes people assume that what's coming up, what the water that's moving through the ground immediately adjacent to a water body is what's coming up through the sediments in the water body as well. So there are direct measurement capabilities there. Again, I'm not an expert on that, but it's definitely an important question from the standpoint that you need to understand what the velocity of that flow rate is in the sediment regime.
Okay, we've got a question here from Juan. What parameters make PAC so much superior to GAC in your example? Has this vast difference been validated against real experiment? So it really comes down to the particle size and the mass transport within the system. So depending on the actual contaminant, those transport parameters may be very important relative to the equilibrium capacity. So in general, it's that fine particle size that's allowing the PAC to perform better because it has improved transport properties. In terms of validating in real world, we've certainly validated that in our lab scale studies, but I'm not aware of a real world head-to-head comparison. John, maybe you have an example of a PAC versus GAC system?
No, it's an excellent question, but all of the pilot demonstrations that we've been involved with have been comparisons of, say, AquaGate plus PAC versus Sedimite. Both of those products are powder-based products. I have not seen a side-to-side comparison of a PAC-based, sand, active cap, versus a granular activated cap layer. I think the important thing to note, though, if you are doing that kind of a comparison in the field, there needs to be some upwelling. So as some of the data that was presented here shown, and what Ken pointed out is that if it's a static system, it's probably not going to make that much difference whether it's granular activated carbon or powder activated carbon. So I know that there's been some installations using sand, granular activated carbon, large installations, but I think that those were performed in areas where there was not that much in the way of upwelling. So they should be fairly similar in that regard.
Thanks, John. What we got?
I think we got them all.
I think we knocked them all off, John.
Okay. Well, I would encourage anybody that's still listening, still on the call, if you have further questions, you have our contact information, and please feel free to call, email, whatever's easiest for you, because we've spent a lot of time and effort on this project together, and I think we have a lot of good data, and we're hoping to get it used, and both Cabot and we at AquaBlok, we communicate with Danny and try to work with him on an ongoing basis to make sure that the information that we're presenting here is fits with what they are promoting, and I know Danny's worked on getting kinetics incorporated into his model, and he's done a lot of updates over the years, and so hopefully this has been a worthwhile activity for everybody, but please contact us.
Thanks for joining us today.